from Beijing Normal University, and he's talking about
fast-valued processes associated with tree-valued processes.
Well done. Thank you.
Thank you. First of all, I would like to thank the organizers, Professor Newman and Professor Shaw, for their kind invitation. It's a great pleasure to be here at this wonderful conference. We have already noticed that the conference is very well prepared. It's impressive that in the booklet we found a brief introduction to each of the speakers. I don't know how they found the information. It's very accurate, right? They know at what year you got your bachelor's degree and which year you got the master's degree and then the PhD degree and where.
It's from KGB.
Oh, I see. Okay. What can we say? Okay, let us start with a very ancient elementary model, the discrete time and the discrete state branching process. I think we can turn off the light, right? I don't know. Okay, at least the screen is much more clear now. Let us consider a family of IID random variables taking values of positive integers. We fix the initial value, the initial random variable x0, then we can use this recurrence formula to define a sequence of random variables. And this sequence actually form a discrete time and discrete state Markov chain. This is the well-known Galton-Watson branching process. Now, in this definition involves a tree structure displayed by the green tree. So the structure is very simple. That if you want to count the number of the total population in the nth generation, you just sum up all the individuals produced by the population in the last generation. Important key in assumption is that the population in each generation have a fixed period of lifetime, that the unit time. So, but in practice, one often need to consider continuous time models. So, of course, the real world has a continuous time. In that case, this structure, this simple structure does not exist. We cannot give a parallel of this formulation to create a continuous time branching process, say. So because at any fixed time, the population may be formed by individuals with different generation. So you cannot sum up the population in such a way as the formula given here. What is more, in practice, we sometimes count a larger population in a huge scale. For example, we may count the people by thousand and thousand, or million by million, even billion by billion. So in that case, your process, the number of the population is no longer an integer. So actually, for convenience, any positive real number can be served as the total population number, right? For example, the Chinese population is 1.3 billion, right? Is that right? So now we have a fraction. not an integer. So it is necessary to consider a continuous time and a continuous model, which can be regarded as a counterpart of the discrete time and discrete state branching process. That is more realistic. However, of course, in the continuous time and the continuous state case, it is more complicated and more difficult than this blue tree shows. So one problem is that in the continuous time and continuous state case, how can we formulate a parallel of this defining definition of the branching model, right? That's a natural question. So to deal with this problem, let us start with the formula again and do some very simple consideration or calculations. Now let us assume that this RID random variable has a finite first moment mu. For convenience, we may use B as 1 minus mu. Now, starting from this formula, on the left-hand side, let us subtract x n minus 1. And on the right-hand side, we need to do the same thing here. And then in this summation, let's subtract the expectation mu. Because there are x n minus 1 terms in this summation, we add mu times x n minus 1. Then this is just a simple variation of the defining formula of the discrete time and discrete state branching process. Now, if you change the time n into k and take the summation as k runs from 1 to n, you get the next formula. This is another formulation of the original formula. And on the left-hand side, you get xn minus x0. So because the terms cancel, a lot of terms cancel each other. And on the right-hand side, you simply get the summation. Now, we may observe the structure of this equality. So having observed this equation, you can imagine that if you want to consider a continuous time and a continuous state parallel of this model, then a natural candidate to consider should be the solution of this equation. Now here, you have x sub n, n is the time. Now here, you have a small x of t, t now is the continuous time. Now here, you have x0, now here, we have x of 0. Here we take the summation as k runs from 1 to n. Now k is the time. Now we take the integral of the time from 0 to t. Now here we take the summation from 1 to xk minus 1. Now here is the integral from 0 to x of s minus. That's the left limit. Now remember here that Kc is a family of RID random variables. Now here we use a Poisson random measure to select those RID random variables, because we know that the atoms of a Poisson random measure are given by RID random variables, right? Another point I need to mention that here we have a centered summation, right? We have a centered summation. So here we use the compensated Poisson random measure that models the centerization. Now this gives the explanation of this term, and this term is simple. You just take instead of the summation, you take the integral. Now then, you may see that this stochastic integral equation is just a continuous time and a continuous state parallel of the defining formula of the discrete Galton-Watson-Brownian process. Now, of course, I may say that the theory of Galton-Watson-Brownian processes has been built up from this formula. Then it is natural to expect that this stochastic integral equation may also serve be a useful tool in the study of the continuous time and continuous state parallel of the Brownian processes. Actually, this really gives us a construction of a family of positive continuous time Markov processes, which is called continuous time and continuous state branching process. Actually, but the solution of this equation does not give all such processes. Now here, by a continuous time and a continuous state branching process rigorously, I mean positive Markov processes that can be obtained as scaling limit of the Galton-Watson-Brownian processes. This equation does not give all such limits. So I shall give another equation in the next slide here. Now, the solution of this equation really gives all possible limits of the Galton-Watson-Brownian processes. Oh, sorry, I didn't mention that although the model of branching processes has a long history, it's a bit surprising that this kind of stochastic equations were only considered a few years ago by Batman and Lagarde and another paper of myself with Dawson. We did the work independently of each other at the same year. This theorem is from the paper with Dawson. Now, there is a most sorry. There is a small modification over the last formula. The difference is the red term. Here, we take the integral with respect to a time-space Gaussian white noise. It is natural because a Gaussian white noise can be obtained from a compensated Poisson noise by a high-density scaling limit, right? So this term can be regarded as a limit form of this term. So you may imagine that the solution of this equation gives actually all possible limits of the Galton-Watson-Brownian process. Now the theorem claims that there is a pathwise unique positive solution to this equation. Then the solution is a strong solution. That means that the solution is essentially a measurable function of the initial state and the two noises. Now, starting from this stochastic integral equation, if you use Ito's formula for processes with jumps, you may find that the solution, of course, with the uniqueness, the solution is a Markov process. Then you may identify the form of the generator of the solution. It is given by this formula. The form of the generator is already known for a long time from a paper by Kawazu and Watanabe in 1971. Now the generator is quite similar. It's very much close, closely related to spectrally positive Levet processes. The only difference is the factor X. So the generator degenerates at 0 at the origin. Remember that we are considering a positive Markov process. So 0 is the the generator degenerates as 0. If one only consider this equation, the pathwise uniqueness is not extremely difficult, because I shall explain that so 0 is the only degenerate point. So we may have use some stopping time techniques to simplify the proof of the pathwise uniqueness. But in the paper, we consider the case where immigration mechanism can be added to the model. In such a case, the simple path can be complicated. But without the immigration, 0 is a trap. 0 is a trap. When the process hits 0, then everything is over. So in such a case, the pathwise uniqueness is easier. Now, you may see that all the parameters in the generator are included in the function defined in this way. All the 3 parameters, B, sigma, and sigma finite measure M. M is the Levy measure. Okay, let me explain in the next slide briefly this term. So, this is the simplest case of the equation given in the last slide. So, a stochastic equation driven by time-space Gaussian white noise. Now, we may write this equation in another equivalent form, driven by a one-dimensional Brownian motion. This model is actually well known that it is called Fehlers-Brownian diffusion. It was found by William Fehlers in 1951. Yes, it is also called as a square root process. You may see that the coefficient of the diffusion term is just 1/2 Hurd continuous. We know that for the existence and the uniqueness of a strong solution of a one-dimensional stochastic differential equation, the 1/2 Hurd continuity is almost necessary and sufficient for the existence and uniqueness of the strong solution. So this equation is already at the terminal of the boundary for the existence and uniqueness of the strong solution. Now, so those 2 equations are equivalent in the sense that if you calculate the increasing process of this continuous martingale and of this continuous martingale, they have the same form. In this sense, those 2 equations are equivalent. But they are not completely equivalent in this sense. Now, if you consider 2 initial values, V2 and V1, you consider 2 solutions of this equation, because now we have the strong solution. So we may start from any number of initial values. We get a lot of solutions. We have a solutions flow. Now, if you consider 2 solutions of this equation and 2 solutions of this equation, then the 2-dimensional processes constructed from those 2 equations, they are not equivalent. They have different joint distributions. But if you have only 1 initial value, those 2 solutions are equivalent. Now, using this equation driven by the time-space white noise, this has this advantage. We may take the difference of 2 solutions of this equation, then the difference of those 2 solutions is still a solution of the equation of the same form. You see, you may have some simple calculations using give shift, spatial shift of the time-space white noise. Then you get a stochastic integral equation of the same form. That means that the difference of 2 solutions is still a Markov process with the same transition probability. Okay, with only a because of the pathwise uniqueness, the solution gives you a comparison theorem. Actually, the solution here is an increasing function. For fixed t, the solution is increasing with respect to the initial value as a function of v. Because it is increasing, then it determines a measure of the positive half-life. Then it determines a measure valued process. Now this measure valued process is actually very simple if you are familiar with the theory of superprocesses. It is a very simple measure valued branching process without spatial motion. Okay, that explains our reason for taking the time-space white noise as the driving noise instead of the one-dimensional Brownian motion. Okay. Now to give a review of the talk up to now. We explained that a natural way to define a continuous time and a continuous state branching process is to use this stochastic integral equation. Now here, W is a time-space Gaussian white noise, and N naught is tilde is a compensated Poisson random measure. Now we may have some additional terms to describe immigration mechanics. In such a case, we have gives us more flexibility in the applications. Now here mentioned several points are mentioned on the applications and some related topics. We mentioned the paper, one paper by Bartun and Lagau. Actually, they wrote a series of papers dealing with the evolution of random curves. Later, it was called the flow of subordinators. The model was introduced in their study of the coalescent processes, especially those with multiplications. Now, if we use this equation, then we can give a unified construction considered studied by different techniques in their papers. Now, there's another model which is called the logistic growth model introduced by Lebesgue in his paper in 2005, and also studied later by Bardou, Van Kobinger, and I don't know, Le, how to read this. This model is just you introduce competition mechanism in the classical branching model given by this equation. Actually, the observations used to create this stochastic integral equation was later used in a paper by Zenghu. He in his paper published in the Annals of Probability last year, he constructed the super Brownian motion as the pathwise unique solution of a stochastic integral equation very similar to this one. Actually, the characterization of the super Brownian motion as the strong solution to a stochastic equation has been an open problem standing for more than 20 years. I mean, when has been several people have been seeking the pathwise uniqueness of a stochastic partial differential equation for the density of the one-dimensional super Brownian motion. But even now, it is still open. Zenghu's work gives a construction of the distribution function of the super-Brownian motion. That means the integral of the density of the super-Brownian motion, not the density. But from his work, we cannot derive the pathway's uniqueness of the stochastic partial differential equation for the density of the super-Brownian motion. Now, the stochastic integral equations of this type were also used in the estimation of parameters of a special kind of continuous state branching processes with immigration, which is known as the Cox, Ingersoll, and Rose model in mathematical finance. Now, in this talk, I'm going to give some explanations on possible applications of this equation to the path-valued processes. The study was initiated by Aldous and Pitman in the 90s and followed by a number of other authors. Okay. So let us recall that the branching mechanism of a continuous state branching process can be given by a function of this form. It contains all the three parameters used in the identification of the generator of the process. Now, starting from this single function, we may give a shift, and then we get a family of functions. For some Q in the interval, or it can be open or can be closed. And anyway, there exists such an interval. For all Q in such an interval, this definition is meaningful. Not for all Q, but at least for Q from an interval of this form. Now, starting from this family of functions, each of them, each of the phi sub Q is a function also of this form. Actually, it can be served. It can serve as the branching mechanism of a continuous state branching process. Now, starting from this family, in the work by Abraham and Delmas, they constructed an increasing tree-valued Markov process indexed by the Q. Originally, Aldous and Pitman considered the discrete time and the discrete counterpart of this model. Actually, Abraham and Delmas just considered the continuous time and the state parallel of the work by Aldous and Pitman. Their process was constructed in a complicated way. Actually, they start from a huge tree, then they cut off the branches of the tree gradually. Then they get a decreasing tree value, the Markov process, and then they reverse the time and then get an increasing tree-valued process. What is interesting is the increasing tree-valued process. Their motivation is to study, is to understand how a finite tree grows into an infinite tree. The phenomenon is like this. When you originally you have a very small tree, and from the small tree, some red flowers grow out. And then those red flowers turn into green leaves, and some new red flowers grow out. And then gradually the tree grows. Finally, at some time, the finite tree will grow into an infinite tree. That means you have an infinite tree. We want to describe how a finite tree turns into an infinite tree. it turns out that the phenomena like this. Then you have finite tree, and then suddenly at some spot, random time, a infinite branch is added to the finite tree. Then you get an infinite tree. So they want to describe the big jump of this tree. So that's the motivation. Actually, the same problem was considered by in the work by Aldous and Pitman.
Is that when theta naught comes into place, does that happen exactly at time theta naught?
No.
No, sorry.
Yes, I'm sorry. Yes, they just constructed the process up to time theta 0. Theta 0 is the time. Yeah. Not quite right. No, not maybe I'm wrong. My original answer is right. They have a random time, not this time. Yeah. Now we have explained that a tree describes the evolution of a population, right? So a single tree corresponds to a branching process. That is the model for population. Now then, a tree-valued process, for each time we have a random tree. A random tree corresponds to a random population. So a tree describes the evolution of a random population. Now then, if you are not interested in the detailed tree structures or genealogical structures of the population, if you are only interested in the evolution of the number of the population, the total number of the population, then the population can be described by a random path. That means that gives the evolution of the total number of the population. Then, by giving up some information, we can describe the population instead of the tree. We may have a path. That gives the total population. Then a tree-valued process corresponds to a path-valued process. Now here you have an increasing tree-valued process. Now accordingly, you have also an increasing path-valued process. A path-valued process has the advantage for being simple and easier to handle. Now this is an increasing tree-valued process. For each Q, you have a tree, T of Q. Now this tree determines a path. So you have xt of Q for T positive. So this is a path-valued random variable. But when T grows, it describes the evolution of the total number of the population. Now as Q increase, you have an increasing tree here. Now you have here you have an increasing path-valued process here. Now, starting from this path-valued process, you may interchange the position of the two parameters. You may write it also in this way. Now here, for each fixed Q, you have a time for when T is fixed, you have here another increasing path. This is another path-valued process. Here you have an increasing path-valued process. Here you have a process of increasing paths, right? Now I want to give a description of the structures of those two path-valued processes. Undoubtedly, if you understand the structures of those two path-valued processes, then you may understand better the tree-valued processes. The advantage of writing the process in this way is that, for example, you can use a lot of techniques to give descriptions of those path-valued processes. But for the tree-valued process, this is a new object. You have only very few tools to deal with it. So we shall see that we have a lot of tools to give descriptions of those two path-valued processes. Okay, I pointed out that each phi sub q is a function of this form. Now the parameters depends on the parameter q, of course, but the sigma does not. The two parameters b and m both depends on the q, the parameter. It turns out that this family of sigma finite mirrors, m sub q, is increasing in q. Because we have here an increasing family of mirrors, then it is a bimirror. Then it determines a mirror of the product space, right? We use the same letter, m, to denote the mirror of this product space. Now, let us introduce the noises. Again, a Gaussian time-space white noise based on the Lebesgue mirror on the product space. Now here, a compensated Poisson-Round mirror with one additional dimension, here dy, or just like dq. So now you have a mirror on the product space. You may use, you may add an additional dimension to the Poisson-Round mirror. Now, we can consider this stochastic integral equation. The only modification is this term. Now you have an extra dimension taking the integral along an interval from 0 to q. Now, for simplicity, we choose a fixed initial value. Now, when q increases, you get a family of solutions. That's an increasing family of path-valued processes. Because for each q, you have a solution. Now you have a family of random path. Now here, this equation just gives a construction of our path-valued process. Now, here, for each fixed q, you have a solution of this equation. That is a Markov process. When q increases, you get an increasing path-valued process. So, of course, you may observe the process in another way. And then I want to, so actually, what remains is not so important. I only claim that we can give some descriptions of those processes using the existing theory, well-established theory. This theorem gives you a complete and explicit characterization of the transition semigroup of one of the two path-valued processes. And the explicit contents of the theorem is not so important. Now, how about the other path-valued process? We also have a similar characterization of the other path-valued process. This is, again, a characterization of the transition semigroup. For this process, we may create a mirror-valued process, as I explained. Now, for this mirror-valued process, we can give a very actually, this formula is not very complicated.
I agree with you.
So this is a martingale problem formulation of the process. It gives explicit characterization of the generator of this mirror-valued process as a Markov process. Here is the list of the references. Thanks a lot.
Thank you.
The talk is based on the last paper. There are some, the basic theory for measure-valued branching processes is developed in my book. The early results on stochastic equations of branching processes and solution flows were described, were studied in those two papers. Thanks a lot.
So, time for some quick questions. I have a question by curiosity. So the original work by Abraham and Delmas, so they construct this the increasing family of trees. So the monotonicity in Q is very important, right? And
yes.
It can be seen from your construction as well, because you construct a joint measure. If you don't assume the monotonicity, then you would expect a signed measure in Q. Is there anything interesting?
That's an interesting, very interesting problem. As far as I know, several people mentioned that they are considering to create such a model. But by now, as far as I know, it is not successful.
Oh. So there might be some troubles.
Yeah, yeah.
If there are no more questions, let's thank again both speakers for their work. So after the hard work of the speakers, let's have a rest. And we come back at 3:20.